last lecture we were looking at the simple harmonic oscillator, and this was in the position representation. So we will continue with the linear harmonic oscillator, the simple harmonic oscillator. And we realized that the equation to be solved, given the Hamiltonian H is p squared by 2m plus half m omega squared x squared. This is the Hamiltonian, and p is to be written as minus IH cross d by dx in the position representation. The equation itself is H psi is equal to E psi. That was the time independent Schrodinger equation, and therefore we had minus h cross squared by 2m d2 psi of x by dx squared plus half m omega squared x squared psi of x is equal to E psi of x. Of course, we realized that there was a part in general which was a function of time, and that was not the time independent Schrodinger equation. We had taken the Schrodinger equation and written the wave function as some psi of x chi of t, and then of course this was the part that depends on x, and chi of t itself had a solution e to the minus iet by h cross, and that is how you define a stationary state, because then the expectation values do not change in time, and mod psi squared again does not change in time, and so on. So we are really looking at stationary state problem solutions to the stationary state wave function in the position representation. And since we have already worked out the harmonic oscillator problem using the abstract operator method A and A dagger and the commutation algebra, commutator A dagger is identity, we can now do it in the position representation, draw parallels between what we got in the abstract operator method and what we will be getting here in terms of the Eigen values and Eigen functions. So we got to a point where I wanted to write this in a more convenient form, and therefore we had d2 psi by dx squared, if I suppress the index x, minus m squared omega squared x squared by h cross squared psi of x, okay, is minus 2me by h cross squared psi of x. And then I said, let us define alpha as root of m omega by h cross, and then indeed this becomes d2 psi by dx squared minus alpha to the 4x squared psi of x is minus 2me by h cross squared psi of x. Now we would like to work in terms of dimensionless quantities. So I can identify a length scale in this problem. You see, this object has dimensions of inverse length, that is the dimension, and therefore if I define an object rho which is alpha x, rho is a dimensionless quantity, and then we can recast this equation in terms of rho. For d2 psi by dx squared would become alpha squared d2 psi of rho now by d rho squared minus alpha to the 4x squared. But then you see, if I bring down this alpha squared, I get a minus rho squared here, psi of x is minus 2me by h cross squared alpha squared psi of x. This object 2me by h cross squared alpha squared is again a dimensionless quantity. I define lambda as 2me by h cross squared alpha squared. And since alpha was root of m omega by h cross, and therefore I have an m omega by h cross here, and so this quantity is 2e by h cross omega. And that is very nice, because now I have an equation in terms of objects which do not have dimensions. I will comment on this shortly, but I now have d2 psi of rho by d rho squared minus rho squared psi of rho is minus lambda psi of rho, and therefore I have d2 psi by d rho squared plus lambda minus rho squared psi of rho equals 0. What is it that we did in the abstract operator formalism, which was the parallel of what I have done now? I have now written things in terms of dimensionless quantities. I have introduced a rho which is dimensionless, because alpha had the dimensions of inverse length, and therefore alpha x was dimensionless. The equation itself is cast in terms of dimensionless quantities like rho and lambda. Now you will recall that when we did the abstract operator method in terms of A and A dagger, the ladder operators, we said that x was root of h cross by m omega A plus A dagger by root 2, and p was root of m omega h cross A minus A dagger by root 2i. This has dimensions of length and this has dimensions of momentum, and therefore A and A dagger themselves were dimensionless quantities. So when we worked in the abstract operator formalism, we worked with A and A dagger and wrote the Hamiltonian as A dagger A plus half h cross omega. And then when I have an equation like h ket n is E sub n ket n, where n is the state of the oscillator and E sub n is the corresponding energy eigenvalue, that is the same as saying A dagger A plus half h cross omega acting on the state n is E sub n ket n. That equation again is in terms of objects which are dimensionless. A and A dagger are dimensionless quantities. I have scaled out an h cross omega, so I might as well just pull that out and say A dagger A plus half ket n is E in units of h cross omega ket n, and if I forget the half as well for the moment, I have A dagger A n is n ket n, where I realize that E sub n is n plus half h cross omega, where n is an integer, and since I have removed the half h cross omega, I have this. So you see, this equation that we wrote when we worked out the harmonic oscillator problem using the abstract operator method was an equation in terms of dimensionless quantities. Scaled out the h cross omega, wrote A and A dagger in terms of x and p such that they were dimensionless, and then you have this equation. The analog of that is precisely this, except that I have written it in the position representation, and therefore I have d by d rho and so on occurring here, and rho squared and so on, but the whole thing has been recast in terms of dimensionless quantities. So it is like writing this equation in the position representation. That is what I have done. So I have psi of rho here. Now when I solve this equation, I first try to find out if I have any solutions for specific values of lambda, and that gives me a handle on solving this equation. So for instance, if lambda is 1, then d2 psi by d rho squared plus 1 minus rho squared psi equals 0. But you see, an equation of this form can be factored and written in a different manner altogether. I have the equation d2 psi by d rho squared plus 1 minus rho squared psi equals 0, and that can be written as d by d rho minus rho, d by d rho plus rho psi equals 0, because this is just d2 by d rho squared psi minus rho d psi by d rho plus d by d rho of anything that comes after that. So that is the same as d2 psi by d rho squared minus rho d psi by d rho plus rho d psi by d rho, and that cancels out. plus psi, and then I have a minus rho squared psi. So that gives me a plus 1 minus rho squared, so which is what I have here. Therefore, the solution of this equation could well be got from this: d by d rho plus rho psi equals 0. But that solution is obvious. If d by d rho plus rho psi equals 0, then that implies that psi is a Gaussian in rho. So d by d rho plus rho psi of rho equals 0 implies psi of rho is e to the minus half rho square. And therefore, that is also a solution of this equation. Since psi is a Gaussian and it satisfies this first order equation, it also satisfies that equation. So I have a solution, I have a definite solution for lambda equals 1. But I know from whatever I have learned using the abstract operator method that there is a Gaussian solution for the equation A on ket 0 is 0. You see, then we wrote A in terms of x and p, wrote p in terms of in the position representation as minus IH cross d by dx, and then we got the Gaussian solution, because if I had started there and I had substituted for A here from this, if I solve for A, I simply have root 2x, let's write down A in terms of x and p. So I have root 2x equals root of h cross by m omega A plus A dagger, and therefore I have root of 2m omega by root of h cross x is equal to A plus A dagger. Then I have an IP again with a root 2, and on this side I had a root of m omega h cross, and therefore root of 2 by m omega h cross IP is A minus A dagger, which gives me A. I can solve for A, and I have A is equal to root of m omega by h cross x plus IP by root of m omega h cross but that was 2A, and therefore I have all this divided by 2. So I have A is equal to 1 by root 2 times this object, and that is fine because I have again made it dimensionless apart from the 1 by root 2 which I need to put in. So now in the position representation, how does this equation look? A on ket 0 is equal to 0 looks like this. In the position representation, let me write this as psi 0 of x and A itself can be written in terms of x. So essentially I am trying to say that root of m omega by h cross x plus IP by root of m omega h cross acting on psi 0 of x is 0, and that means, but root of m omega by h cross is alpha. So I have alpha x plus I by root of m omega h cross, p is minus I h cross d by dx, psi 0 of x equals 0. So I have alpha x plus root of h cross by m omega d by dx, psi 0 of x equals 0. That is the same as saying that gave me an alpha downstairs. So 1 by alpha d by dx plus alpha x psi 0 of x equals 0. In terms of rho, which is alpha x, that is simply d by d rho plus rho psi 0 of x equals 0, which is exactly what I have here. So it is good to draw a parallel and understand how exactly the abstract operator method, when written in the position representation, will give me this. I started with writing A ket 0 is 0, but if A is written in terms of x and p, and P itself is minus IH cross d by dx, I simply get that equation with a solution which is a Gaussian solution. So that is one thing that I have learned, that for a specific value of lambda, lambda is equal to 1, the solution is Gaussian. And then by inspection I see the following. Go back to the general equation. Let me look at the asymptotic form of psi of rho, because I know that it has to satisfy boundary conditions. The wave function has to vanish sufficiently fast, has to go sufficiently fast to 0 at spatial infinity, that is as rho goes to plus minus infinity. But when rho goes to plus minus infinity, this object overpowers this, and really the value of lambda becomes immaterial. So in order to study asymptotic behavior, that is as rho goes to plus minus infinity, I might well take lambda to be 1, and if I did that, I can see that psi of rho should go as e to the minus rho squared by 2, apart from other functions of rho. I will call it u of rho. The dominant behavior for rho going to large values is e to the minus rho squared by 2, goes as e to the minus rho squared by 2, and that is all that I needed to know. Now I can substitute this for psi, this solution for psi, recast the differential equation as a differential equation for u, find out u, and then I know the full solution, the wave function for the simple harmonic oscillator in the position representation. So that means the following. Let me write psi of rho as e to the minus rho squared by 2 u of rho. So that means d psi by d rho is u prime of rho, first derivative of u with respect to rho, that is psi prime, but I need psi double prime of rho. That is a u double prime of rho. I am now going to have a second order equation in u. That is what I have from the first term. So this is what I have for d2 psi by d rho squared, and then I substitute it back there. I am going to have an equation which involves u double prime and u prime, both of them. I have a minus rho e to the minus rho squared by 2 u prime of rho, and the same thing out here, so that gives me a minus 2 rho, and therefore I have the equation itself becomes d2 psi by d rho squared gives me u double prime of rho. I am going to pull out an e to the minus rho squared by 2, that is a common thing in all of them, and the asymptotics are dictated by e to the minus rho squared by 2. So that is u double prime of rho minus 2 rho u prime of rho. So I have taken care of these terms. And then I have plus rho squared e to the minus rho squared by 2 u of rho, and then I have minus rho squared e to the minus rho squared by 2 u of rho. So there is a cancellation there. And then of course I have lambda, so I have out here plus lambda psi of rho, and I have pulled out an e to the minus rho squared by 2, therefore I have a lambda u of rho, that is there. So I have already taken care of all these terms except this one, which is a minus u of rho. So this object is equal to 0. So let me write this in a convenient fashion. I have u double prime of rho minus 2 rho u prime of rho plus lambda minus 1 u of rho equals 0. So this is the equation for u, second order equation, which needs to be solved. Once I solve for u, I can put that back in psi of rho, just multiply it with the Gaussian e to the minus rho squared by 2, normalize it suitably so that the wave function obeys the probabilistic interpretation. It is normalized to unity, and then I have my answer. But you see, to solve this equation, I will use the fact that u of rho, we are now working in function space. I will use the fact that u of rho can be expanded in terms of polynomials of rho. I can write it as a polynomial of rho. So therefore, u of rho, let me try this solution. It is a summation over Cs rho to the power of s. Again, I am interested in the asymptotic behavior. So definitely I need to worry about s taking large values, and s could perhaps take all values. So let me say s starts from nu Cs rho to the power of s. Some value nu, does not matter the small values. I am worried about the asymptotic value. So let me substitute that there, and therefore I have summation over s Cs. So u prime of rho is summation over s Cs s rho to the s minus 1, which gives me u double prime of rho is equal to summation over s Cs s times s minus 1 rho to the s minus 2. Now substitute this. I will keep this for later perhaps. So when I substitute this back, I have summation over s Cs s times s minus 1 rho to the s minus 2. That is what I have for u double prime, minus 2 rho u prime. U prime is simply summation over s Cs s times rho to the s minus 1 plus lambda minus 1 u that is equal to 0. So now here, if indeed this should give me 0, it is clear that every power of rho, the coefficients corresponding to every power of rho should vanish. So let us compare, let us write down the coefficient of rho to the power of s. So for that, let me redo the first term, call s minus 2sp. So it is summation over p, suitable summation. I am only interested in the asymptotic value. So when s goes to infinity, p also goes all the way to infinity. So that is p plus 2, s is p plus 2. So s minus 1 is p plus 1. Rho to the power of p, that is the first term, and I can go back to calling p as s because that is summed over, that is just a dummy index. That is my first term, minus 2 summation over s Cs s rho to the power of s. So I am just trying to pull out coefficients of rho to the s plus lambda minus 1 summation over s Cs rho to the s is 0. And therefore I have Cs plus 2 for any s, Cs plus 2 times s plus 2 s plus 1 is equal to 2 Cs s plus lambda minus 1 Cs. Therefore, Cs plus 2 by Cs is 2s plus lambda minus 1 divided by s plus 2 times s plus 1. Now this is a good thing to know because we are interested in what happens for large values of s. The asymptotic behavior is going to be dictated by this ratio, and one wants to see if the series converges at all. So let us look at this ratio. For large s, this ratio was as 2 by s because I have a 2s, that is negligible compared to that for large s, and here I have an s squared, that is the leading term, and therefore I get an s by s squared, it is a 1 by s. So for large s, this goes as 2 by s. But I know of another series, I am now trying to find out the solution for u of rho as a function of rho. I know of a series which for large S has this asymptotic behavior, and that is unfortunately the series solution for e to the rho squared. If I expand e to the rho squared, so maybe it is good to put down this equation somewhere, d2 psi by d rho squared plus lambda minus rho squared psi equals 0. And lambda was 2e by h cross omega, and rho was alpha x. Alpha itself was root of m omega by h cross. So there we are. So if you look at the series e to the rho squared, let's write this as summation over c as rho to the power of s, you find that for large S it goes as 1 by s. And that is very unfortunate as it stands, because that is like telling me that u of rho is essentially e to the rho squared, and therefore psi of rho is e to the rho squared times e to the minus rho squared by 2, which I guessed from the asymptotic form when lambda was 1, and this is therefore e to the rho squared by 2, which is unfortunate because for large rho it blows up. But I want psi of rho to go to 0 as rho goes to infinity. So I cannot let terms for large S survive in this series if at all I hope to get a solution. So the only way to handle this is if the series truncates at some point, so that the coefficients corresponding to large S simply do not contribute. Some value of S where the series truncates, and therefore the summation over S does not go all the way to infinity, but gets stopped somewhere else, somewhere at a lower value, at a finite value. And if that happens, then clearly I do not have to worry about the asymptotic behavior and predict that to be e to the rho squared. So let us see how exactly this series will truncate. I do not want that. So one way of solving the problem is to look out if the series truncates somewhere, and that is possible because if 2s is equal to lambda minus 1, oh, this is 2s minus lambda minus 1 here. If 2s is equal to lambda minus 1, then I know that the series truncates. But since s is an integer, lambda must be equal to 2n plus 1, where n is an integer, positive integer. And then if s is equal to n, the series, when s is equal to n, the series truncates. So the summation over s goes from the lower value, whatever it is, all the way to n, where lambda is 2n plus 1, where n is an integer, positive integer. So that is a possible way of handling this problem, and indeed that is the correct way of doing it. But if lambda is equal to 2n plus 1, go back to the definition of E. E is h cross omega by 2 times lambda. So E is n plus half h cross omega. So you see this is very intimately connected with each other. The fact that the asymptotic behavior of psi should be admissible, the fact that psi should go to 0 for large rho, for large values of rho and therefore x, puts a constraint on lambda because the series has to truncate, and that in turn tells me what the eigenvalues are. So the eigenvalues are of the form n plus half h cross omega, and in principle n can be 0, 1, 2, 3, anything. And when n is equal to 0, it tells me that lambda is equal to 1, and that is the lowest value that n can take because s has to take positive values. So lambda is equal to 1 really corresponds to the ground state of the oscillator, And indeed we saw that the ground state of the oscillator, the wave function in the position representation, is a Gaussian wave function, and that is how things get linked up with each other. In any case, going back here, suppose there is some value of n where the series truncates. That is very nice, because then u of rho is simply summation over s all the way to n, c as rho to the power of s, and that is it. So C n is not equal to 0, but C n plus 1 etc. are 0. It is a finite series. Now look back at this, and if I do that, what kind of equation do I have here? This equation is essentially the same as the equation satisfied by the Hermite polynomials, because the equation for the Hermite polynomials is like this. Suppose Hn of rho is the Hermite polynomials. The solution of the equation Hn double prime of rho minus 2 rho Hn prime of rho plus 2n Hn of rho equals 0 is the Hermite differential equation. These are polynomials in rho. Hn of rho is a polynomial in rho. I briefly mentioned the properties of Hn of rho in an earlier lecture, said that in function space they could form a basis. The function space that we are considering here for the harmonic oscillator problem is clearly L2 minus infinity, infinity, because rho takes values minus infinity, infinity. So u of rho, the solution for u of rho is essentially Hn of rho apart from some normalization constant, and therefore u of rho is some normalization Hn of rho, and therefore I would like to call this Un of rho. Lambda itself is 2n plus 1, and therefore the n is brought in here. So we could well write Un of rho minus 2 rho Un prime of rho and a Un of rho there. This lambda, okay, so that is what I have. So this is some normalization which I have called, I could well call it n, Hn of rho, and clearly the normalization would have a 1 by root pi 2 to the power of n factorial to the half from the orthonormality property for Hn, which I just now wrote, and therefore this is what I should be having for Un of rho. I need Un of x, and since rho is equal to alpha x, Un of x is alpha by root pi 2 to the power of n factorial to the power of half Hn of x. So this is what I have, and this is normalized to unity. The UNs form an orthonormal basis set of functions, but now going back to psi, I now write psi n of x, because for a given value of n and therefore lambda and therefore E, I have a certain wave function, and that is given by this object Un of rho, which is essentially Hn. So let me not write the normalization, it is some normalization n Hn of x times the Gaussian e to the minus x squared by 2. The Gaussian takes care of the fact that the wave function goes to 0 sufficiently fast at infinity, space infinity. The Hn of x themselves arose because the series had to be truncated in order that the wave function was an admissible wave function. Not every wave function which is square integrable can be a solution to our problem. It is only those wave functions which satisfy the boundary conditions imposed by the physical requirement of the probabilistic interpretation, that wave functions must be normalized to 1, and therefore the probability of seeing the system in the given region of space is 1. It is that's going to bring out an Hn of x here, and therefore I have eigenfunctions of the oscillator given by psi n of x with the energy eigenvalues given by n plus half h cross omega. So in this method of working out eigenvalues and eigenfunctions, there are some crucial points which are worth noting and which we will be using in subsequent problems that we will consider. Wherever possible, we will go to dimensionless variables. In this case, we went to rho and lambda, where rho itself did not have the dimensions of length. X did, and alpha had dimensions of 1 by length, and therefore rho was dimensionless. Similarly, lambda did not have dimensions because lambda was e by h cross omega, 2e by h cross omega. So we will do that always, and that, as I said, connects up with the abstract operator method, because we wrote that in terms of a's and a daggers, which were dimensionless objects. In fact, I had explicitly illustrated that a on ket 0 is equal to 0 really turned out to be the differential equation with lambda set equal to 1 here in the case of the position representation. These are the wave functions, but I know that these wave functions must have definite parity. I know this because of an earlier argument that I had given, that the Hamiltonian for the harmonic oscillator, for the one-dimensional oscillator, commutes with the parity operator, and from that I had earlier shown that the wave functions would have definite parity. The eigenstates of the Hamiltonian would have definite parity, either positive parity or negative parity, and that there is a complete set of common eigenstates of the parity operator and the Hamiltonian. Now that you can verify right here, because the Hns can be written in the following fashion. H0 of x is 1, H1 of x is 2x, H2 of x is 4x squared minus 2. So you see, this has odd parity, this has even parity, that has even parity, and so on. E to the minus x squared by 2 anyway is an even parity state. When x goes to minus x, e to the minus x squared by 2 does not change sign, and therefore these wave functions have a definite parity. It is clear that psi 0 of x, psi 0 of x, psi 2 of x, and so on are even parity states. That means psi 0 of minus x is plus psi 0 of x, and so on. And psi 1 of x, psi 3 of x, psi 5 of x are odd parity states. That means psi 1 of x is minus psi 1 of minus x, or psi 1 of minus x is minus psi 1 of x, and so on. This property is reflected by the fact that psi n of x is essentially Hn of x, and the Hns themselves have even and odd parity, like I have shown here. Now if you look at the wave function and have a schematic plot of these wave functions as a function of x, you can schematically see the following. So if you take psi 0 of x, remember that this is the same in my notation as x0, where a on ket 0 was 0. This written in the position representation is psi 0 of x, and if I plot psi 0 of x versus x, get a Gaussian in x centered at x is equal to 0. Then if you look at psi 1 of x, and psi 1 of x is x1 in my notation when n takes a value 1. goes to 0 at infinity, goes to 0 at plus infinity and minus infinity, but that is antisymmetric, that is an antisymmetric function of x, and therefore you can see that it has odd parity. Look at the number of times it cuts the axes. Psi 0 of x does not cut the axis, it just goes all the way to plus minus infinity. There is no finite value of x where the wave function vanishes as far as psi 0 of x is concerned. As far as psi 1 of x is concerned, it has one point where it vanishes, it is a node. A node is a point where the wave function vanishes. Now look at psi 2 of x, that is an even parity state. That is an even parity state. The wave function goes to 0 at space infinity. It is a symmetric wave function, cuts the axis at 2 points. These are the nodes. This in my notation is x, n is equal to 2. Quantum optics, I would call it the 2 photon state. I have written the 2 photon state in the x representation, if I were talking in the language of quantum optics. The case of the simple harmonic oscillator, I would simply say that it is the second excited state of the oscillator. So we have this. Now the number of nodes is increasing. The ground state had 0 nodes. The first excited state of the oscillator has 1 node. The second excited state has 2 nodes, and so on. And why does the number of nodes increase with energy? Now that is something that we can see rather easily, because in general the number of nodes would increase with energy for the following reason. The contribution to the Hamiltonian comes from p squared by 2m, and therefore I have p psi star. I am trying to find out the expectation value of energy, the contribution from the kinetic energy. Since that had a p squared by 2m, and I can pull out the 1 by 2m, I would just have p psi star p psi, and this is all a function of x, and therefore I have dx, where I have psi of x and p itself is minus ih cross d by dx. So the expectation value of energy is integral minus infinity to infinity minus ih cross d psi by dx star minus ih cross d psi by dx. But that, apart from constants, involves a gradient operator, so that is essentially an integral over grad psi mod square dx. And since the gradient operator adds to the energy, the more the gradients, the more the number of times you have to go up and down, there is an increase in energy, and every time you cross a node, you go down, you go up, whereas here that does not happen. Here you go up once, here you go up twice, and so on. Therefore, as the number of nodes increases, there is more work done. The gradient operator brings in a larger contribution, and therefore the energy levels, as the energy levels increase, you find that the number of nodes increases. In the case of the oscillator problem, the number of nodes increases by 1. The nth excited state of the oscillator has n nodes. That means it cuts the x-axis, the wave function cuts the x-axis n times, and that is what you see here. There is a last point that I want to make before I close this lecture, to connect up the operator method, the abstract operator method that we had with whatever we have written here. We know that in the abstract operator method we had shown this. Barring constants, it is clear that A on ket n is essentially ket n minus 1. So let us see if this is really true. I know that psi 0 of x, that corresponds to ket 0, is e to the minus x squared by 2. It is a Gaussian, and then there is a normalization which I will forget for the moment, but it is essentially a Gaussian, and then psi 1 of x is the Hermite polynomial h1 of x, which is 2x e to the minus x squared by 2. That is again apart from normalizations. So let us see if A in the position representation acting on psi 1 really gets it to psi 0 of x. So A, you will recall, is d by dx, d by d rho plus rho, and this is supposed to act on this object. So let's worry about d by dx plus x acting on psi 1 of x. This quantity, let us evaluate this. That is the analog of A on ket 1. Of course, I am forgetting constants, I am just trying to see the general pattern. So that is e to the minus x squared by 2 plus minus x squared e to the minus x squared by 2 plus x squared e to the minus x squared by 2, and that gives me the Gaussian. So you see A on ket 1 is essentially ket 0, they essentially, because I have not put down the constants, this is good enough for me to see it. Similarly, if you look at A dagger on ket 0, you can check that that gives me ket 1. In other words, A dagger acting on e to the minus in the position representation acting on e to the minus x squared by 2 takes it to x e to the minus x squared by 2, and that is what you have plotted here. This is e to the minus x squared by 2 schematically, this is x e to the minus x squared by 2, and so on. So we have checked therefore that the operator formalism exactly matches with the position representation formalism of the harmonic oscillator problem. Now it is a matter of convenience. If all we need are the energy eigenvalues and the energy eigenfunctions, we could well work with the operator method, provided we are not interested in the position, provided we are not interested in the manner in which the oscillator oscillates in time, what are the instantaneous values of position and so on. If that is a matter of interest to us, then it is more convenient to write things in terms of the position representation. Otherwise, all these results could have been got, perhaps with less work in some sense, if we use the abstract operator formalism. And now we have established that both of them are equivalent methods of solving the same problem. In the position representation, the energy eigenstates of the oscillator, the Hilbert space is a separable space, it is a denumerable infinity of eigenstates, and each one of them happens to be representable essentially as Hermite polynomials, appropriate Hermite polynomials producted with a Gaussian, suitably normalized. That is a wave function in the position representation, and the corresponding eigenvalues of course are n plus half h cross omega, where n takes values 0, 1, 2, 3 and so on.